The the separable differential equations was the was the first actual technique, but this particular one involves some sort of new trick that we're learning. So the other one you separate it and you integrate it. This one you actually it requires a little bit more work, and so but officially this is our second technique that we're learning. And again, we're still dealing with first order differential equations. And so here's a step-by-step process, and maybe we can try to remember what some of these things are. Like, what does it mean for something to be in standard form? How does it look like? Yeah. Yeah. I don't know if that's what we want, though. Maybe the word standard form shouldn't be it. Um, Generally, that's how we get everything in standard form if you have more than one that's higher than the first order. But I think if it's a first order differential equations, I think standard form that we want for this one should be um, the derivative plus the function itself times whatever it's being multiplied by is equal to any other extraneous functions. So this is your first order linear, and then you identify your p function, and that's going to be the function that's being multiplied with a y. And then the integrating factor is e to the integral of p of x dx. And then from here, you're going to multiply the differential equation. Okay? So in the example that we're about to do, we have to identify, I guess, because we're changing from y, dy, dx, we're looking at dr, d theta. It might be good to figure out which one's the independent variable and which one's the dependent variable. And I think the independent variable is the variable in the bottom of the dy, d whatever, d something, d whatever. And so what we want to do is we want to eventually solve for r of theta. So theta is going to be our independent variable. And your dependent variable is r. So I think this is already written in standard form, kind of written in standard form. And if r is your dependent variable, that's like your y, then that means your p of x, or in this case p of theta, is equal to secant. So that's what we want to identify in the second step, and we're going to go ahead and find the integrating factor. So integrating factor is going to be e to the integral of secant theta d theta. Oh boy, do we know what that is? E to the ln of secant theta plus tangent theta. And remember that this is an integral, so in general we want to find arbitrary constants coming from the integral, but in this particular scenario, that arbitrary constant will eventually come out in our second integral, so we'll just ignore that. Yes? Yeah, you can think about it that way. Yeah. So this is, you're multiplying by something just to make it look like a product rule. So, yeah. Um, all right, so I suppose this simplifies. The e and the ln would undo each other. This is just secant theta plus tangent theta. And so that's what we want to multiply by. We want to multiply by mu. Now, of all the steps that you can skip, I suppose this is the step that you can skip if you want. But I'm going to write it down anyways for the first couple of times. And then as we do this later on, I'll skip the step where we're going to write it out, multiply everything out, and then look at it as a product rule. So you got secant theta plus tangent theta times dr d theta is equal to r secant, oh, not equal to, plus r secant theta is equal to secant theta plus tan theta. Oh, I need that one here too, right? Yeah. Sorry. I'm going to multiply this. This is why I want to skip that step, because there's a lot more writing than what's needed. Anyways, the right-hand side is the cosine theta times secant theta plus tan theta. And then the whole point in doing this integrating factor is to realize that the left-hand side is actually a product rule of something. And the product that we're looking for is mu secant theta plus tan theta times r, or the dependent variable. We could say r of theta, we'll just leave it as r. And then this will give us an opportunity to simplify this a little bit. Secant is 1 over cosine, and tangent is sine over cosine. So if we multiply cosine through, we're just going to get 1 plus sine theta. Okay. So now we will integrate both sides. The left-hand side is a derivative of something, so the integral of the derivative is that something, secant theta plus tan theta times r. And eventually we'll divide out the secant plus tangent, and then we'll have r by itself. Meanwhile, on the other side, we will integrate with respect to theta. Is this a plus or a minus? Minus cosine theta. And then here's where you want to throw in the plus c. So with respect to theta, the integral of 1 is theta, and then the integral of sine is negative cosine. So we're essentially done here. The function that we want is going to be theta minus cosine theta plus some constant divided by secant theta plus tan theta. So we've explicitly solved for this. If there was a, what's that called? An initial condition, we would solve for that arbitrary constant, and then rewrite our final answer. But in this case, we just have a general solution, so we should be all good. Yeah. No. I mean, you could put it there, but we're just going to ignore it. It's not needed. Any questions? Okay. I see a couple of other problems up here. Should we pick one of these other problems, or should we go back to the book and find another one? What do you guys think? Let's go back to the book. All right, we'll do one more, and then we'll do an initial condition, or you just want to jump to an initial condition? Let's do an initial condition. Let's do it. All right, the initial conditions come around in number 25 through 36. You got one of these, 28 through 36? Any 29? 29 is fairly simple in terms of integrating. Are we good with that? All right. I think that was one of the examples that I had. And what we have here are a bunch of constants. So that'll simplify our, uh, our integrals. So identify the independent variable and the dependent variable. So it looks like the independent variable is t, and then I is a dependent variable. I is a function of t. So L, R, and E are constants. And we want to write this in our standard form for the first order linear. So not a big deal, but we should probably divide by L. And we're going to probably okay to assume that L is not equal to 0. So let's go through this. Di, dt. We want I of t, by the way, so we know what the independent variable is. We know what the dependent variable is. Di dt is equal to r over L times I. And so that gives your p of x function, or p function, is equal to e over L, which is a constant, right? Nice and simple. So we can find our integrating factor. Mu is equal to e to the integral of r over L. We're integrating with respect to t here, because t is our independent variable. And it looks like we have e raised to the r over L t is going to be our integrating factor. Now that we know our integrating factor, we'll multiply both sides by the integrating factor. This is going to give us e to the r over lt times di dt plus e raised to the r over lt times r over L times I is equal to e over L times e to the r over lt. Okay, left-hand side is a product. E to the r over lt times I is equal to, and then the right-hand side, oops, let's write d dt of the left-hand side of the product. And then the right-hand side is just that, e over L times e to the r over lt. And so we're going to integrate both sides. And then we're going to get e to the r over lt times I on the left-hand side. And then the right-hand side, we have a constant, and we have an e to some power. So the antiderivative is going to be e to the r over lt times, or divided by r over L. After you do u substitution, right, that constant will just come out. So you simplify a little bit, and then you solve for I. I is equal to e over r times e to the r over lt plus our constant divided by e to the r over lt. And sometimes people simplify this and distribute and do all that kind of stuff. And so we have e over r, and then these things would cancel. And then I have a c times e over r over lt with a negative power so that it can be written up in the numerator. And then you can also identify as x gets larger, or t gets larger, this thing goes off to 0. So this is a transient term. Oh, I didn't resize my. Didn't resize my paper. Not gonna look good in the notes. Ah. Still a little bit outside of our notes. I can resize that, but I'll just make room. All right. Is that okay? Are there any questions? So we good with this technique? Of course, you need to practice. So you can do homework or you can pull out more problems to practice on and get good at it because we'll be learning more techniques. Questions? All right, let's try another technique. And this time we're going to take a look at a differential equation in a slightly different way. Um, we've seen different forms of the differential equation with the y primes and the dy dx's, but you can also take a look at the differential equation where the dy and dx get split up. And so we're actually looking at a couple of differentials. And so that's what we're going to do now is we're going to examine a differential equation that can be written as something with a dx plus something with a dy. So it actually looks like it got separated. Before we do that, let's backtrack and, well, not backtrack. If pretend you're in Calc 3 or if you have taken Calc 3, then try to remember the differential. If you haven't, then here's a quick overview. If you have a function of two variables, you could take the differential of that function, and the differential of that function would be a couple of partial derivatives. And so it's a partial derivative of the function with respect to x. And what makes it a differential is that you tack on the little dx after that. And then the partial derivative of the function with respect to y, and then you tack on the dy. So differentials are those things that people don't usually kind of gloss over in Calc 1, and so it kind of gets lost in the mix when you start talking about it in Calc 3 and differential equations. But they exist, and this is what we have. Now, if you have your function set equal to a constant, then that derivative of that, or the differential, if you take the derivative of both sides, is going to give you a df dx times dx, or partial f with respect to x dx, and partial f with respect to y dy is equal to 0. So that is a kind of equation that we're going to look at. So a differential expression that looks like some function with an x and a y in it times dx plus another function with an x and a y in it times dy is called an exact differential in some region. And so from there, we can define a first order differential equation that looks like that exact differential equal to 0. I guess this should be boldface, an exact differential equation. So it's called an exact differential equation if that expression on the left-hand side is a differential of some function. So in this definition, we kind of steered away from the Calc 3 discussion up on top. And then what we want to know is that we want to know if we have a differential equation, does it fit that Calc 3 model? In other words, is it an exact differential equation? Well, the quick way to check if it's an exact differential equation is a criteria that, again, is discussed in Calc 3. And in Calculus 3, you guys have studied, for those people that have studied Calc 3, there's the idea of the mixed partial derivatives. You take the partial with respect to x first and then with respect to y. That's a second order partial derivative. And then you take the derivative with respect to y first and then with respect to x. And it turns out that if you have a nice function, those two things are equal to each other. So this criteria in the theorem here in the bottom is a criteria to check if you do have a nice function or if a function actually exists whose differential is equal to the left-hand side of the differential equation. So if you're looking at this page and hearing me say blah, 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 that's okay. Because all you really need to know is the term exact differential equation and the criteria, and then we're going to talk about how to solve for it. Okay, we don't need any Calc 3 stuff. So let's just take a look at some examples and see if we can jump in and solve for some exact differential equations. I guess the first thing we need to know is that we have to check if something is an exact differential equation. And if it is, then we can solve for it, maybe. And if it's not, then we're out of luck. Yeah.
Like a potential function?
Yes.
Okay.
If it's equal to 0, conservative potential functions and all that stuff. So if you're familiar with that, then that's great. That's kind of like what this is. And if you're not familiar with that, don't worry. We'll do some examples and it'll be crystal. Do I have examples? I don't have examples. I have to go to 1 through 26. 2.4. So the first thing we should do is we should probably figure out that there are differential equations of this form that might be exact, and there are differential equations of this form that might not be exact. So let's take a whole bunch of these and then just check them to see if they're exact or not exact. I think that would be a good way to start. I'm just going to grab a whole bunch here and then check it out. So let's just say for now we're going to check. Maybe I should type instead of write. You guys understand it better? Yeah. All right, let's check to see if it's exact or not exact. The criteria is right over here. We have to identify our m function and our n function. And then we need to take the derivative of the m function with respect to y, and then take the derivative of the n function with respect to x. So if you think about it, the m is the one with the dx. Take the derivative of that with respect to the other variable, y. And then the n is the one with the dy. Take the derivative of that with respect to the other variable, x. And then that's how we can check if it's exact. So let's identify the m and the n functions for the first one. And let's take the derivative of the first function with respect to x. And when you take the derivative of this with respect to one variable, you're going to look at the other variable and pretend it's constant. Right? That's how we do partial derivatives. And there's a whole theory behind it with limits and stuff, but we're not going to do that because we're not assuming that you've taken Calc 3. And then n, what? Can't draw an n. Do you write an n? Oh, sorry, I already messed up. We want the m with respect to y. Let's try that again. We want the m with respect to y, and that's 0. And then we want the n with respect to x, and there's no x here, so the derivative of that is 0 also. So that we can say that this is an exact differential equation. By the way, you can write this as the differential equation that we know of, like a dy dx, by just treating the dy and the dx as if they were variables, and write it as a ratio. All right, let's do number 2. We want to find m with respect to y, and that looks like it's going to be 1. We want to find n with respect to x. This looks like it's a 1, but there's a negative in front of it, so I think this is a negative 1. So this is not exact. You get the feel for this? Let's skip number 3. Let's do some trig. Let's do number 4. So the first function is your m function. That's the one with the dx, and we want to take the derivative of that with respect to y. So the derivative of sine is cosine y minus, now this is where you try to remember the differentiation rules for partial derivatives. The sine x is a constant. The whole thing is constant. And then the y is your variable. So if sine x is a constant, let's pretend that that's equal to 5. What's the derivative of 5y? Just 5, right? So the y kind of disappears, and then you just have the derivative of that is just going to be sine x. So that's your m function. That's your m function taking the derivative with respect to y. Now you need your n function taking the derivative with respect to x. So derivative of cosine x is sine x, positive or negative? Negative sine x. Here x is a variable, y is constant, and so this will go away again. So the derivative of cosine y, derivative of x cosine y with respect to x is cosine y. And then minus y, the derivative of y with respect to x is 0. So it looks like these two match up. So this must be exact. Okay. Are we good with identifying exact and non-exact functions? All right. Let's take one of these exact functions that we found and see if we can solve for this. Let's take number 1 first. Start off easy. All right. Now we've shown that this is an exact differential equation. And what they're saying, the theory behind this is that if this is an exact differential equation, then this must have come from a function of x and y. In other words, this must have been a dz that must have come from a z function. And since this was equal to 0, then this c function, the z function, must have been equal to a constant. So that was a theory in the first thing that we looked at when we looked at exact differential equations. Okay. So back to Michael's, right? Michael's comment about this being a potential function. We're going to solve for this as if it was a potential function. So what we're saying here is that this m function moving. This m function, yeah. Yeah, it's equal to some constant. And we don't know what the constant is unless we have the initial conditions. So the differential comes from taking the derivative of the function with respect to x and multiplying it times dx. So that means this function m, which is right next to dx, must be the derivative of the function with respect to x, this unknown function that we're looking for. And the derivative of f with respect to y is that function that's next to the dy. So that means the n function must be f of y, or f sub y. And the subscript means you're taking the derivative with respect to that variable. So what we want to do is we want to try to recover f. And so we're going to take the integral of the m function with respect to f, or with respect to x. So we're eventually looking for f, the original function f, and we're saying that one of these two functions over here, the first one, was the derivative of the original function f with respect to x. So we want to take the antiderivative of that with respect to x. I'm going to write a couple more that probably is not necessary, but I'll write it down anyways. So the m is equal to the fx, which is equal to 2x minus 1. And I want to take the derivative of that with respect to x to get that potential function that we're looking for with respect to x. So just like the derivative, when you take the antiderivative with respect to x, we're going to treat the other variable constant. And so we're going to, there's no y's in there, so we don't need to worry about treating anything constant. So we have the antiderivative is just going to be x squared minus x plus some constant, right? Now, I was going to put c in here, but let's take a look at the structure of f. F is a function potentially of x and y, right? So when I take the derivative of f, if I have a y by itself, then that would have disappeared because y is a constant with respect to x. So instead of just putting c for any constant, there's a possibility that I get a function of y, which if I had taken the derivative, it would have disappeared. So when I'm trying to recover that, I want to account for that fact that I might get another function of y in here. Okay, does that make sense? Yes. No, because you can assume that the real constant can be part of that y function. So the c of y could be like sine y plus y squared plus 4. It's all in there. All right. The way the book does it is that they go from here and they take the derivative of this with respect to y and then try to set it equal to the n function. But I like to go back to the potential f function and see if we can grab the potential f function from the n. So n is f of y. And we would have gotten that n function by taking the derivative of the original function with respect to y. So to try to recover the original function, we're going to take the antiderivative with respect to y. And here's what we got. I got the integral of 3y plus 7 dy, and that's going to give us 3 halves y squared plus 7y. And again, there's a possibility that we're going to get another function of x because x is constant. Now these two c's over here, so sometimes they write this as g of x and h of x, or g of y and h of x. So let me go ahead and change that. So now what you want to do is you want to see if there's anything that matches up and see what the original function might have been. And this is where my method gets a little bit tricky versus the book's method, where I think it's a little bit more straightforward. But I like to look at this and compare what functions are missing and what functions are supposed to be accounted for. So it looks like I have an x squared minus x plus g of y. Well, the g of y must be this whole set of functions over here, right? And then on the other hand, I have this 3 halves y squared plus 7y plus h of x. But h of x must be this business over here. So it looks like if I just combine these two functions, then I have my original f of x. So what's that? I mean, that's if I put this together, x squared minus x plus 3 halves y squared plus 7y, then that must be my original function. And what you could do is you could take this function and take the differential of this function. So take the derivative with respect to x, and then attach on a dx. Take the derivative with respect to y, and attach on a dy, and see if that looks like our differential equation from the beginning. Okay? I'm not going to do it because it does, unless I did something wrong. Only. We'll talk about the constant in a minute, but there's going to be a constant in here somewhere. Yes, that's where the constant comes in. So what we're saying is that this comes from the differential of this function, and then on the other side it's equal to 0. So that means the solution is going to be x squared minus x plus 3 halves y squared plus 7y is equal to 0. Nope, equal to c. And that's your arbitrary constant. Now, you may be interested in trying to solve for y, because usually that's what we want. But sometimes in these cases, it's kind of hard, almost impossible, maybe impossible to solve for y. So in some of these cases, we would leave our answer as is and say, this is, what kind of solution is this? Implicit. This is an implicit solution where x and y is an implicit function of x. And you can't solve for y for a bunch of values. But if you need to, you might be able to solve for y if you restrict yourself to a specific domain, a small domain. Okay. By the way, do you know how this thing looks like? Anybody? Anybody who's taking Calc 3? You might know. Yeah, sure. An ellipse. Let's just take a little quick timeout to draw an ellipse. If you want to figure out where exactly they intersect. Can't graph. Oh man, it's gonna get all mixed. So remember that we get a family of functions. So when we take this and draw a whole bunch, here's our family of functions, at least 3 of them. And then notice that it's not a function, right? It doesn't pass the vertical line test. But if we need to, let's say we have our initial condition is 2 comma, what is it, 4.5 or whatever that is, then we can say we'll just focus on one of these curves, and then we'll just take the positive part or something, a piece of that curve, so that it would actually be a function. Yeah. Oh, I don't know. Should be. Is that going to mess things up? Oh, plus. Oh, it's close. Thank you. Oh, wait. It's not close. Yeah, it's on the other side. Anyways, you get the picture. Get it? Picture? Where is it? There it goes. Yeah, so so it's not a function. So that's why it's defined implicitly. And you get a family of them. And you would get a specific function if you're able to solve for that C. And you would be able to solve for that C if you have initial conditions. Okay? Whoa. Any questions? Let's put this in our notes. Cool. So this is going to work if you have an exact differential equation. If you don't have an exact differential equation, there's some comments and information about multiplying it by some integrating factor, but that gets a little complicated, so I'd rather not worry about that. Yeah. Yeah, if you want to figure out where the center is, how elongated it is and stuff like that. Yeah. You'd complete the square and then write it in the standard form of an ellipse. All right, let's do another one. Is there one with initial conditions? Here you go, 37, 38. Oh, they have integrating factors. We're staying away from integrating factors. Up here, 21 through 26. Let's pick one. Which one do you guys want to do? 25. Yeah. Okay. I have to find a quicker way to come up with more pages here. We should probably check to make sure it's an exact differential equation before we continue. Although it should be. Exactness. Be careful. Sometimes they get tricky and they switch the dx and the dy around. So make sure you look at the dx, and that's the function next to it is going to be the m function. And to check for exact, we want the derivative of the m function with respect to y. All right, so there's y squared times cosine x. Cosine x is constant, so I'll leave the cosine x, take the derivative of y squared 2y. So don't bother with the product rule. I know it looks like a product, but the cosine x does not have a y in it. You're taking the derivative with respect to y, so it's just a constant. The next one is 3x squared y. Y is your variable. 3x squared is constant. So that's just 3x squared, and the y's go away. And then this is going to be 0. 2x, derivative of that with respect to y, there's no y's in it, so the derivative of that's going to be 0. And now n with respect to x. Derivative with respect to x, there's a 2y is a constant. Derivative of sine is cosine. Derivative of x cubed with respect to x is 3x squared. And then ln y, the derivative of that with respect to x is 0. Guess we don't need to put the 0 there. But it looks like it is exact. We can proceed with our method. So once we know that it's exact, we're confident that we should be able to find the original function. What we're going to do is we're going to take the derivative of your first function m with respect to the antiderivative of your first function m with respect to x. And we have y squared, which is constant. The derivative of cosine x is positive sine, right? 3x squared y minus 2x x. So all this with respect to x. So back over here, y squared is constant. So the derivative of the antiderivative of cosine is positive sine, so this remains positive. And here y is constant, so this is just going to be x cubed. And then minus x squared plus that c, but we're going to call it g of y to make room for the possibility that there's a y in there that would have disappeared if we took the derivative with respect to x. And now with the other one, n, let's take the derivative of n with respect to y, the antiderivative, 2y sine x minus x cubed plus ln y dy. And that's equal to, with respect to y, this is going to be y squared sine x is a constant. X cubed is a constant. And the antiderivative is y. Now, if you say 1 over x here, I'm going to have to zap you with something so that you'll remember it's not. Is it 1 over x? It's what? Oh my goodness. It's not 1 over x. Now, you guys think of that? You guys would think of that. I could see it. Yeah, that's a derivative. Yeah. I don't know. Integration by parts or something. This is the beginning. Oh, I don't know. Thank you. I know. Especially if you memorize them with U's. All right, so the antiderivative ln x is x ln x minus x. So the antiderivative ln y is y ln y minus y. And then you have the make this provisions for the x-only terms, which would have disappeared had you taken the derivative of your original function with respect to y. So let's match it all up. What's there? What's not there? These match up, so I'm for sure going to have a y squared sine x in my function. I'm not doubling it, right? I'm not adding this. I'm just matching the terms up to say, okay, which terms did I have for sure? I have these two terms for sure, x cubed times y. And I don't have an x squared in my second function, but that x squared must live over here in h of x, right? And likewise, I don't have this y ln y minus y in my first function, but that must live in the g of y. That qualifies for a function that's all y's. So they both must exist in my original function. So let's put them both down. Okay. Now this is not your answer to your differential equation, right? This is just the function that we found. Now the answer to your differential equation is this function equal to a constant. So answer, let's say general solution, because we have a particular solution, we have an initial condition that we'll plug in, but for now, let's just say our general solution is this y squared sine x minus x cubed y minus x squared plus y ln y minus y equal to a constant. Remember, we're starting off with this thing equal to a constant, and then we took the differentials and we had that equal to 0 in our differential equation. So now, to get our particular solution, we use our initial condition, which I think is y of 0 is equal to e. So that means when x is equal to 0, your y is equal to e. So we're going to put e in for y and 0 in for x. And then solve for c. So sine of 0 is 0. 0 times e is 0. This is 0. E ln e. Ln e is 1. So this is just going to equal to e. And then this is e. So c must equal 0. So particular solution. You rewrite this whole thing again and set it equal to whatever constant you found. In this case, we found 0. Okay. I don't know. Suppose we have the power to graph it. Y squared sine x minus x cubed y minus x squared plus y ln y minus y equals 0. I don't know if it comes back down. Oh, wow, look at that. Oh, okay, I'm not doing anything anymore. Ah, what's happening? Stop. It doesn't though, because the first curve looks like it's still going. What is it? Control C, break, escape. Ah. All right, let's just. Oh no. Oh, there it goes. Whew. All right, let's draw it again. Oh, wait a minute. I lost something. Minus y equals 0. Yeah, so it doesn't pass this right here, this part Looks like it fails a vertical line test. And I was kind of squishing it down. Okay, so there. Oh, I thought it started to go on its own again. Anyways. Yeah. Interesting graph. So the family of solutions is that if we would have gotten C to equal to something else, then we would have gotten a slightly different curve. And then C is equal to something else, and we've got a slightly different curve. So depending on what C is equal to, you're going to get different curves. There's subtle differences in them. But that's a solution, and it's implicit. It's an implicit curve because it's not necessarily a function. But again, you can take a small piece of it if you need to. Okay. So I don't know if I should go into. Yeah, let's not. Okay. On Tuesday we're gonna have a quiz, and I'm gonna quiz you on separable and integrating factors differential equations. Okay. So the first question will be a separable differential equation, and then the next question will be a first order linear differential equation where you have to find an integrating factor. Okay. And do you have homework due this Sunday? I think you have homework due this Sunday. Yeah. All right. Okay, so that's it. Have a good weekend. Good luck.